Hello, my name is Mukund Krishna and I'm the Senior Manager of Technical Marketing at Empower Semiconductor. Empower Semiconductor was founded to solve the power density challenges across applications and has the first and only commercialized IVR or integrated voltage regulator product. Today, I will be taking you through the topic of addressing power delivery challenges for FPGAs in data-intensive accelerator applications. In this discussion, we will start by doing a brief examination of the data sphere and the overall trends driven by it that affect power management in general. Subsequently, we consider why FPGAs have and will continue to play a bigger role in data centers, specifically accelerator functions. Majority of this discussion will then focus on the major sources of power consumptions and how IVRs are perfectly positioned to provide the best solutions to address power delivery challenges. Finally, we consider a real-world FPGA-based example to quantify the benefit of an IVR solution. If we consider all locations where data is created, captured, or replicated, such as data centers, the edge, and endpoints like PCs, phones, and IoT devices, collectively called the data sphere, market studies suggest that we're at the start of an explosive growth, reaching 175 zettabytes by 2025. Hence, if we look at the corresponding increase in the global energy demand, we expect to see an 18% growth from just data centers and networks. However, equipment and infrastructure form factors and overall sizes do not have room to grow at the same rate, which means in the same given form factors as today, we expect to see a lot more data and a lot more heat. And this leads us to among the most important challenges ahead of us. Energy security has remained one of the critical factors for modern civilization. Data center power usage effectiveness, which measures the ratio of the total energy of a data center to the energy delivered to its computing equipment, is heavily impacted by cooling costs. Estimates put it up to at 40%. A common method is water-based cooling, which is also a precious resource. Advanced cooling methods exist but require high capital and maintenance costs. All of this highlights the fact that there is a singular focus that is required on reducing energy consumption and related costs of the data sphere, if we are all to live peacefully hereafter. As the Internet of Things expands rapidly all around us, data centers are rapidly evolving from data storage and fetch models to real-time processing of extraordinarily large volumes of data in the form of speech, images, and video requiring AI inference. Movement of data in real time for an AI experience requires very low latency and high throughput, driving exponential need for network port speeds compared to compute cycles. Traditional CPU-only data centers built to perform a variety of tasks with the same resources then get forced to spend an outsized amount of resources on just networking. As a result, hardware acceleration has become the de facto method of handling specialized tasks such as networking and AI inference. Therefore, specialized hardware built for repetitive tasks are much more efficient than using generalized CPU resources for the same tasks. However, it is also true that the type of workloads are rapidly evolving and changing, adding new functions all the time. Hence, programmability is a critical feature for these hardware accelerators. FPGAs are ideally positioned to take advantage of these needs, having evolved from simple programmable logic circuits to highly integrated combinations of high-performance logic, memory, high-speed interfaces, and even analog functions. Studies have suggested FPGA accelerators have 20 times higher throughput versus standard CPUs and 4 times higher than even some GPUs. Project Catapult from Microsoft is one example where a reconfigurable compute layer using FPGAs is used between the CPUs and the network to form what is called hardware as a service. To understand the methods of addressing power delivery challenges, we first need to establish the sources of power consumption and the factors that influence them. A common notion for managing power consumption is simply to target the efficiency of the power conversion function itself, but in reality there are other important factors. FPGAs, like most other CPUs, have logic cores, and in general the power consumption sources for these logic cores can be broken up into 3 sources. Static and dynamic power consumption are both dependent on the voltage, with the former being proportional to the voltage driven by leakage and the latter being proportional to the square of the voltage and the frequency reflecting switching activity. The third and non-trivial source is the power delivery network or PDN losses, which is proportional to the square of the current delivered as well as directly proportional to the efficiency of the power management supply. Having established the factors and sources of power consumption, we now know that then an effective power delivery solution must manage the voltage to these logic cores, as well as target power conversion and delivery efficiency. First, we start by looking at dynamic voltage scaling. It helps to define what voltage scaling refers to. Voltage scaling is the process of varying the supply voltage to a digital processor dynamically, that is, at runtime based on real-time performance needs. There are a few varieties of implementation, but the effect is the same, which is to deliver only the minimum voltage required to perform the tasks at hand. Conversely, when high-performance processing is not required for a time interval, the minimum required voltage is reduced. By dynamically managing this voltage, the effective power consumption can be reduced. The dominant effect is that the dynamic power consumption, which reduces as a square of the voltage. For maximum effect, it is combined with a corresponding reduction in frequency. In today's logic cores that have hundreds of billions of transistors switching at very high frequencies, the effect of reducing that switching power is tremendous, especially when combined over hundreds or thousands of such logic cores. There have been numerous studies on DVS, and one such study, to illustrate the point, shows that 30% energy savings can be gained with effective implementation of DVS techniques. DVS or DVFS is a popular concept that has been widely implemented in standard CPUs for power management. FPGAs are not thought of as generally requiring these methods. However, as discussed earlier, FPGAs are cementing themselves in the hardware acceleration space and demonstrate better performance than CPUs and GPUs for specialized tasks. So it is also worth highlighting that FPGAs today do come with the ability to perform dynamic voltage scaling and reap the benefits. The example Xilinx UltraScale Plus platform illustrated here suggests anywhere from 10 to 38% reduction in power consumption through voltage scaling. First, we look at DVS performance between a traditional DC to DC converter and Empower's IVR. For the same 200 millivolt transition, the IVR performs the transition in 33 nanoseconds, 1,000 times faster than the 30 microseconds that the traditional DC to DC converter does it in. This dramatic increase in speed is driven by typically 2 orders of magnitude frequency higher of the IVRs than standard DC to DC converters. The main concept to understand here is that while the voltage is undergoing a transition from the initial to the final state, the logic core of the processor cannot start operating at the higher performance state. Conversely, if a processor has knowledge of an impending high-performance task that is scheduled, the transition must be scheduled in advance, resulting in the entire voltage transition being the overhead. Which leads to the question, why is this overhead important? As we just discussed, the entire transition time of the voltage is called an energy overhead. This is because the logic core is being underclocked until the voltage reaches the final state and settles. Underclocking refers to the operation of the core at a voltage that is higher than and a frequency that is lower than necessary. In other words, the overhead is wasted static and dynamic energy, since that energy is not being used towards performance at the higher voltage until that final voltage is reached and is stable. This equation states that the energy overhead due to underclocking during the transition time is an integral of the dynamic power loss of the CPU and the static power loss of the CPU at the slower frequency. Therefore, a shorter transition time will result in lower energy overhead. With an IVR, the voltage transition can be scheduled just tens of nanoseconds prior to when it is required, minimizing the time when the core is underclocked. To sum it up, IVRs can provide additional energy savings from DVS techniques by almost eliminating the overhead involved in the transition. Next, we look at the load transient or load step performance of IVRs and how they contribute to energy savings. One of the important reasons behind the constant movement of logic implementations to smaller geometries is the capability to switch these transistors faster. Today, we're at multiple gigahertz of clock speeds. Combined with the ability to pack hundreds of billions of transistors together, this can result in a very large power consumption in a very short period of time, as all these transistors start switching simultaneously. In order to manage the power consumption within sustainable limits, which then enable the usage of cost and area efficient power management, Techniques such as power gating and clock gating are used to allow subsystems to operate at the highest power state, only when required. This technique is extremely common in battery-operated or portable devices and is quickly being adopted in data center systems. FPGAs have been applied in a myriad of applications and hence have architectural options to allow the devices to go into lower power states such as block RAM, clock gating, and time division duplex. Conversely, for low latency performance, these blocks transition from low power or off to high power state within fractions of microseconds. Today, FPGA core rails are specified with load step rates up to 100 amp per microsecond, and other rails are at up to 10 amp per microsecond. The primary idea is to highlight the capability of IVRs to handle these ultra-fast load steps, especially when compared to standard DC to DC converters and modules. Shown here are measured results comparing the mPower IVR and a standard DC to DC. For an 8 amp load step in 230 nanoseconds, which is effectively about 32 amps per microsecond, the IVR demonstrates a 15 millivolt droop shown in the blue plot, and the standard DC to DC demonstrates a 70 millivolt droop shown in the green plot. The difference in overshoot when a load release occurs as fast is even more stark, driven by the large amount of capacitance that's required for the standard DC to DC converters. System designers are forced to factor the lowest voltage point and account for it, since the recovery time for the standard power management is in the order of microseconds, which is an eternity for very fast microprocessors. But the question to really answer is, why does that performance difference matter? As hinted earlier, a system designer must take into account all variations that are possible in the stability of the voltage supply to these high-performance logic cores. The reason for this is twofold. The primary is the need to operate at the lowest voltage required in order to minimize the static and dynamic power consumption. The second is to ensure that the variation in supply voltages does not exceed the maximum rating for a given core and at the same time does not drop low enough to cause a brownout. Over the years, power management solutions have excelled at minimizing the variations due to initial tolerance, load and line regulation, and even ripple. However, load step related droop can be around 10% as illustrated in the previous comparison, making it the biggest factor to consider. From the previous example, a reduction in droop of 55 millivolts can result in being able to position the nominal supply voltage lower by that amount, resulting in 12% dynamic power savings. If we examine the trends in core supply voltages, what used to be around the 1 volt region has already started to reach 0.4 volt for high performance ASICs, owing to the fine geometries and reduction in power. As a result, the percentage savings in dynamic power from better load step performance can reach 20% or more, which is a non-trivial amount. Next, we look at the benefits of the ultra-high density integration that IVRs are capable of. All but one type of power management devices today fall into this category, where there's an active device, such as a controller with power stages integrated, that operate in conjunction with a host of passive components such as inductors, capacitors, and resistors. The lateral area and height occupied by such a solution typically dictates that it be placed laterally away from the power consumer. By definition now, we have a lossy path that drops voltage, expends power in the form of PDN losses, and also has the effect of slowing down any fast current steps as seen by the power management. The common method to address high-frequency load variations is to use low-value, high-frequency capacitors, as shown here. An IVR solution like the mPower IVR encompasses the entire solution in one package that is much smaller and thinner than the alternative traditional solution. This now opens up the possibility of co-locating the producer and consumer of power literally next to each other. A vertical delivery model is now made possible, greatly reducing PDN losses and associated voltage droops. An important side effect is that the PDN-related inductance also reduces, allowing the fast load steps to be observable by the IVR. Conveniently, the IVR's high bandwidth, facilitated by its ultra-high switching frequency, allows a fast response, as discussed in the previous section, and thereby allows the reduction or removal of the high-frequency capacitors. It is beneficial to go into a deeper examination of the entire power delivery network's frequency response to quantify the benefit of high bandwidth and proximity. The first chart on the left illustrates an example of a typical power delivery system using a standard DC to DC converter. Such a converter is assumed to operate in the 1 MHz switching frequency, which places its bandwidth in the few hundreds of kilohertz range. The light green line shows the voltage regulator's output impedance response. To extend the bandwidth of the network, the external capacitors are utilized, whose response is illustrated by the blue curve. The SoC or processor packages on die capacitance for high frequency filtering is shown by the teal plot. The effective impedance of the entire network is the red plot. There are some large side effects, which are the LC resonant peaks. These resonant peaks can be challenging, especially when there are periodic current steps in the system at those frequencies, causing the noise due to those current steps to be amplified, becoming rogue waves. In theory, one could attempt to flatten the impedance, but there is limited flexibility given the capacitance requirements of such a converter. In contrast, let us examine an illustrative IVR-based PDN response. The first thing to note is that the IVR's bandwidth is about 100 times higher, which allows it to inherently respond to fast load steps. As a result, the amount of output capacitance required is at least 10 times lower, lowering the number of components and associated costs. The second important effect to note is that by placing the IVR much closer to the load, the associated PDN inductance is also lower by about 10 times. This allows the IVR to observe and respond to the fast load steps and minimize the high frequency capacitance requirements at the load. To summarize, the high bandwidth of an IVR allows it to lower the impedance of the network using fewer components, reducing cost and space, and the proximity of placement lowers the inductance of the PDN, reducing the need for high frequency decoupling at the load. A real-world example is used to estimate the benefits from using an IVR solution for an FPGA application. The Xilinx UltraScale Plus family is positioned for data center network acceleration with the integration of logic cells, DSP slices, memory, Ethernet, PCIe, and transceivers. It includes options for voltage scaling and features load steps in the 100 amp per microsecond to 10 amp per microsecond range. The IVR solution shown is for a system voltage of 12 volts, wherein a 1.8 volt supply is generated by a high efficiency traditional DC to DC converter, followed by Empower IVRs to fan out the power to the different domains required. To illustrate the benefits, we first look at alternatives. A traditional DC to DC discrete solution would provide the highest input to output efficiency with 89% and 117 components and 820 millimeters square. We start with an assumption that we're dealing with a system that does not have the ability to fit such a solution. Hence, an examination of other alternatives to shrink the solution leads to modules that increase frequency and shrink the output filter components while keeping everything else the same. There is a 20% reduction in size from the shrink and co-packaging of the IC and inductor. However, by raising the frequency and reducing the inductor size, the switching losses increase, leading to a 42% increase in the power loss, which is not desired. We may be able to fit such a solution, but it does increase power loss. The IVR solution illustrated earlier leads to a 55% smaller solution than even compared to modules with only 20 components. Even a two-stage solution, the input to output efficiency is marginally higher or comparable for a much smaller area than modules. However, if the system power savings from DVS and voltage guard band savings are factored in, the efficiency would equal that of the DC to DC converter that we started with. So effectively, you have a solution that is much simpler with 83% fewer components, much smaller in 1/3 the area without sacrificing system efficiency. Going back to the problem statement, we define the need to reduce the power consumption by the global data sphere. Assuming IVRs are utilized to reduce energy consumption in data centers by at least 10%, which is a modest amount by 2025, the projected savings per year by 2025 could almost be 300 terawatt hours and 150 million tons of CO2. As FPGAs get utilized at an increasingly fast pace in the data sphere, IVRs can provide the tools required to address the power delivery challenges. A flexible solution like an FPGA requires an equally flexible power management solution to power it, like the Empower IVR, whose flexibility and configurability are illustrated in the family of parts that show they can be configured to suit a variety of application needs by splitting the available current into a number of different outputs. Thank you for listening to my presentation.